In 1.8, we're going to be looking at domain and range of functions. And we've already kind of mentioned domain and range in previous sections, and we talked about ordered pairs and tables, and we looked at how to find that domain and range. Now we're going to dive a little bit deeper into more notation and looking at kind of how to represent our answers in multiple ways. So to start out, there's just a general note about set builder notation and interval notation. We've already kind of hit on this, and so we won't emphasize all of it, but I want to make sure it's all here for you. The first one is set builder notation. Set builder notation is a method of specifying a set of elements that satisfy a certain condition. It takes the form X such that, then there is a statement about X, which is read as the set of all X such that the statement about X is true. So we always have it with brackets here. There's an up and down line here that we say such that. And then here's our statement or conditions stating what all the X's need to be like. So when we're working with this, it's just kind of a compact way to represent what all of our answers may look like. But we could write it in another notation, just depending on how the question is stated. We could write it in interval notation. Interval notation is a way of describing sets that include all real numbers between a lower limit that may or may not be included and an upper limit that may or may not be included. The endpoint values are listed between brackets or parentheses, and a square bracket indicates inclusion in the set. A parentheses indicates exclusion from the set. So this right here is the inequality representing the numbers between 4 and 12 such that equal to 12, but they do not equal 4. This is the interval notation to reflect that same amount of solutions. Notice there's a parentheses here, just like there's not an equal to, and there's a bracket here because there is an equal to. Both sets of notation represents the numbers between 4 and 12. So as we move forward in this section, you're going to see set builder notation and interval notation as we go. So I want to look at the first example here. It says describe the intervals of values shown below using inequality notation, set builder notation, and interval notation. So first of all, I know it's kind of hard to see with all the black lines. I want to note that we're looking at the area here to here and shade it. And then we're looking at starting at 5 and going off all the way in this direction to infinity. And so as we're looking at a problem like this, we want to represent all the solutions that we see here on the number line. And so I'm going to just drop down here to the side and write the different notations. First of all, if we wanted an inequality notation, I would say, let's see, we're going between 1 and 3. And you'll notice it's shading in at 1 and 3, so I'm putting an equal to under both of those. And we can see that we're going from 5 all the way up. So I would say, and, actually, they'll say, or 5. And we want all the numbers bigger than that. So we would say X is greater than 5, and we would not put a bar underneath it because there's a circle there. Now, using this inequality notation helps us to set up our set builder notation. And on the set builder notation, we're going to use the inequalities, and we're going to say X such that it is between 1 and 3, including 1 and 3, or X is greater than 5. And so you can see knowing your inequality notation helps you to set up your set builder notation. And then the last one is our interval notation. And it's probably the most compact of all three. We want to go from 1 to 3. And we use square brackets because you can see we have solid dots there and it's equal to. Union with, I want to go from 5 up to infinity. So I'm going to say 5 of the parentheses because I'm not including it, comma, positive infinity, and we always use parentheses on the infinity. Now this is just one example. There will be problems where you might have to work it out, express your answer in interval notation, just depending on how this one's worded. This one just had the basics of writing things with notation. So the next example here is it just wanted us to be able to match the set builder notation to the interval notation. And so it would be beneficial in your notes that if just as we write them, instead of just writing the set builder notation and then like A, B, or C, because that wouldn't make sense. If you're doing handwritten notes, write both of them beside each other so you can see they're the same. If you're printing these notes before the lecture, you could just mark them accordingly because you have all the answers here. And so let's look at the first one. If we want x between A and B and we want it to include A, we would need a square bracket. We do not want it to include B, so we would need a parentheses. So you can see that that would be the letter E, where I have a square bracket on the A and a parentheses on the B. And again, if you're taking handwritten notes, I would write this notation and then this notation right beside it. If you're using my template and printing this before the video starts, then you could just connect them or write the E out beside it like you see here. Next, I want to look at one at x such that x is less than or equal to b. So all my numbers are going to be less than b, but could be equal to. So this would be letter D. Notice it would be equal to b and going off to negative infinity. So D would be the best answer for the second one. The next one looks similar to A, but I want you to notice between this top one and this third one, it's equal to on both A and B. And so that means the next choice would be B because I want to have a square bracket on the A and a square bracket on the B to include those values. The next one is similar, but notice the difference. This has an equal to, this one does not. So it means I'm going to have a parentheses on the A and a bracket on the B. So I come over here and I can see that A is the correct answer choice. Now I want x such that A is less than x. So that means x is going to be bigger than A. I'm not going to include the A, so the correct answer would be H. It's not equal to, so I have a parentheses going off to positive infinity. The next one I want to make sure you understand, this is x such that x, this stands for an element of, and this stands for, I'm just going to jot it out to the side, all real numbers. Math people are lazy. We like to use symbols and shorthand notation to represent things. And so instead of writing all real numbers, we just use kind of an R with an extra stem in it. You can see up here above, when I was going off to an infinity, I didn't write an infinity in the set builder notation, but then I came over here and I did have an infinity in the interval notation. So we need some way to say between negative infinity and positive infinity, everything possible. And so this is our shorthand for that. And so G would be the correct answer for this one. So I'd make sure you kind of have a note of this if you see that letter again. The next one is A is less than X is less than B. Similar to these up here, but you notice there's no equal to underneath these. So we're going to have a parentheses on both of them. A is less than or equal to X. So we are going to have a bracket going to positive infinity. So F would be the correct one for this one. X is less than B, so we need negative infinity to B. It's not equal to, so we're going to maintain that parentheses there, so this would be the letter I. Now, I did summarize these as we go forward, but this was just a great example out of your textbook that I wanted to grab, and it had you matching up which interval notation goes with which set builder notation. So on the next page here, I just went ahead and grabbed another good example from the text, and I wanted to specifically copy and kind of paste this in there because I want you to see what was given and what your answer choices were. It says, which of the following graphs represents the following set? X such that X is greater than or equal to negative 4. So I want things that are bigger than negative 4 but also equal to it. Well, this would be the case of a bracket. If it didn't have the equal to underneath, it would be parentheses. When they're graphing on the number line, this also can be represented as a colored in dot. And so if I know I need it to be equal to, I can already see these are not going to be good choices for me because they're not equal to. Then I'm going to say X is bigger than the negative 4. And so I'm going to have shading to the right. I want numbers bigger than negative 4. So this second one ends up being the correct answer choice for this problem. So I just want to kind of emphasize what could be given, what kind of answer choice you might see. And then this next page, especially if you printed out these notes, is a really great page because I just grabbed this from the text. I wanted you to have like a one-page go-to to help you with understanding inequalities, interval notations, and how they can be described. And so I just kind of grabbed this table from the textbook. Again, it's printed off in the notes on page 3, but it does come from your textbook. So just reference that. And if you're taking handwritten notes, just put in there good table in textbook or see notes so that if you need a good go-to for figuring out what that interval notation may look like, given an inequality, etc., then you have that as a good resource. The next page, what I want to do is part 2, domain of functions. I want to go back and I want to look at our parent functions that we already addressed in the previous section, and I want to go deeper into domain and range. At this point, we've only done domain and range in dealing with ordered pairs and tables, and we learned that, I'm just going to jot this at the top here, domain is all the possible x values. And we also know already that range is all possible y values. And so if I'm looking at domain and range with a graph or an equation, I need to be able to understand how to grab that information from it. Our parent functions are very handy because I've told you, all equations are going to relate back to a certain parent function. If we understand domain and range in the parent function, we can better understand domain and range in the given function. And so just kind of reviewing the different functions, it's really a good test question that you'll see on exams of, maybe state 4 of the parent functions. We're going to go over 9, so just remembering 4 of them. And so I want to kind of emphasize you need to know equations and what the graphs look like. And in this section, I want to make a good resource or notes of what the domain would look like. So the first one is your constant function, f of x equal to c. You can see it's a horizontal line. So our domain is negative infinity to infinity because you can see left to right is our domain. So maybe up here I'm going to put arrows. This is my left to right, and this is my up and down in referring to domain and range or looking at a graph. And so you can see that the domain on this first one, left to right, I'm going to use all possible x values, so its domain is negative infinity to infinity. Now its range is literally just the value c because it's only using one y value for the entire function. Now the constant function is not really one of my most favorite parent functions because it only describes a horizontal line, so the rest of them are a better example of parents. The next one, remember this is your equation y equal to x. This is just your linear function. Notice left to right, I'm using all values, so my domain is negative infinity to infinity. And then up and down, there's no y values I'm not using, so negative infinity to infinity is my range. The next one is the function y equals absolute value of x. You'll notice it has a V shape, absolute value, see that V shape. Left to right, there's no issues, and that's what I'm looking for, problem areas. Areas where those x values would not occur. So left to right, my domain is negative infinity to infinity, but range, my up and down, you can see that here and below, there's no values whatsoever. There's no representation of a graph. We have no y values. So my range is actually a bracket 0, comma, positive infinity, because you can see all your values of y would exist above the y-axis. The next one is y equal to x squared. And so you can see left to right, no big deal. This does get wider and wider as it goes out. So my domain would be negative infinity to infinity. My range would be 0 to positive infinity because you can see it's starting at 0 and going up from there. So there's my range. The next one is y equal to x cubed. And you'll notice left to right, this is going to get wider and wider as it goes down. So we're going to have negative infinity to infinity. Top to bottom, the range is going to be negative infinity to infinity because, again, there's no problem areas going up and down. The next one is the function y equal to 1 over x. So first of all, just looking at the function, you can see that I'm plugging in values into the denominator of a quotient function or a fraction. And the number in the denominator, it can be anything it would like to be except 0. We can never divide by 0. So you'll see that x-wise, there is no 0 values. This is going to create something known as a vertical asymptote. It's going to come down, but it's never going to hit that y-axis. It's going to go up. It's never going to hit that y-axis. And so my domain is negative infinity to 0, parentheses, union with 0 to infinity. The same is true for y. There's no way that fraction is going to equal y, so you can see there's no y value of 0. And so my range is the same for this one. So again, this is a great example of when you're looking for problem areas within a function and figuring out the domain and range.